Now we have arrived. We have learned about the topologies of amplifiers that are discrete devices already. This will be a summary of the important points. That is, from what we have analyzed, we can see that MOS amplifiers usually provide an infinite input resistance. This is a good point, right? This is an advantage. It's better than the BJT amplifier. And BJTs for the most part provide higher voltage gain because the GM of a BJT is usually higher than that of a MOSFET. This is precisely why, for discrete amplifier circuits, BJTs are generally considered more popular. They are simply easier to handle than discrete MOSFETs, primarily because MOSFETs are typically quite susceptible to damage from static electricity. Whereas BJTs are not nearly as fragile, they are just not that sensitive to those kinds of electrostatic discharges, making them much more reliable for these types of circuits. To that extent, for example with MOSFETs, we can destroy them with static electricity from our own bodies. Therefore, when handling MOSFETs, you should hold them by the body rather than the pins. Furthermore, there is a wider selection of BJTs available as discrete components, whereas MOSFETs are mostly found integrated into IC circuits. And if we observe from what we've done so far, we can see that the common source and common emitter configurations provide the highest gain, and it also depends on the gain we require. We could implement it as a single stage, a cascade, or even connect 3 stages together. Because if we cascade them, the gain will be the product of each stage's gain, and adding Rs to the common source circuit makes it more stable, although the advantages of the common source might not be very apparent. If it's reconnected in a common emitter, we can see that the performance improves significantly. For example, the input resistance also increases. The only thing is that the gain decreases, and the bandwidth for the operating range can handle higher frequencies, that's all. Most of the disadvantages, or what we lose, is the reduced gain, but as I said, the reduced gain isn't that big of a deal. We prioritize stability more. If the gain drops, what can we do? Just connect 2 stages and the gain will increase. It's not that difficult, right? And for the low input resistance, there is only one topology, which is common gate and common base. If you recall, for common gate, it's 1 over GM, right? And for common base, the input resistance is Re. This unique characteristic makes it exceptionally suitable for its specific demanding applications, and notably, its effective operating range also extends quite comfortably into high frequencies. Now, when we consider the source follower or the emitter follower configurations, they are primarily and most commonly utilized as voltage buffers. This means they are strategically placed between a high resistance source and a low resistance load. Essentially, they are inserted directly between a load with a relatively low impedance value and a signal source that possesses a high resistance value, which helps to prevent signal degradation and ensures optimal power transfer across the circuit. Most of the time, the voltage buffer is usually found in the output stage, meaning it's in the final stage. Once we have successfully amplified the signal to the level that we need, we then place a source follower or an emitter follower at the output stage to drive the load. That is how it is typically used in practice. So, moving on, this is a summary table, and as you can see, there are quite a lot of variables involved here that we need to consider. This specific section is dedicated to BJT or bipolar junction transistors. Please do not feel intimidated by these complex-looking numbers just yet. I promise I will break them down and summarize them for you again in a moment. Think of this as a comprehensive review of everything we have covered so far in our lessons. I am going to start a fresh page right now and attempt to summarize all of this clearly. You might be feeling a bit shocked, perhaps thinking to yourself, wow, are there really this many variables to keep track of? But I assure you, it will all make sense once we lay it out. But actually, there are techniques for memorizing them. Is it necessary to memorize them? Not really. If you memorize them, it will help make analysis easier. I usually memorize them because in the end, if you connect 3 amplifier stages and try to draw a small signal circuit, it starts to become difficult to analyze. But if we memorize these formulas, memorize the positions of the resistors, it will help make our analysis easier. Now let's take a much closer look at this entire setup. To make things significantly clearer, I am going to divide the analysis into 2 distinct sites, okay? We are going to walk through this process very carefully, step by step. We will begin our discussion by focusing on the MOSFET first. If you recall from our previous lessons, we initially started by learning about the fundamental structure of the common source amplifier. The circuit diagram for this configuration looks something like this. It is connected to a positive supply voltage, which we call VDD, and then it is connected down through the resistor RD directly to the drain pin, while the other side of the circuit goes down to the reference ground. Now regarding the signal flow, the input signal goes directly into the gate pin. Let me just write that up here for you. Yes, the input signal goes into the gate pin, and then the resulting output signal comes out of the drain pin. It is configured just like this, okay? And we have already performed the small signal analysis. Everything is done. We really need to remember this. This is one point you have to keep in mind, okay? The R input here is equal to infinity because for a MOSFET, there is essentially no current flowing into the gate pin at all. Now looking at the R output, this specific R value is simply equal to RD. It is a fundamental relationship that you should definitely commit to memory for your analysis. And what else is there? So this is exactly what we have been searching for all along, isn't it? Let's break down this fundamental relationship. The voltage gain of this amplifier stage is defined as being equal to the negative transconductance, or GM, multiplied by the total effective resistance that is seen between the drain pin and the AC ground. Now why is there a negative sign? That negative sign is crucial because it indicates a phase inversion, meaning the output signal is 180 degrees out of phase with the input signal. And when we talk about the total resistance between the drain and AC ground, we are considering the parallel combination of all resistive elements connected at that node. By understanding this specific product of GM and the total resistance, we can accurately predict how much our signal will be amplified, which is the core goal of our circuit analysis. I usually remember it this way. I think this part here is... I'll write it down below so it stays on one line, okay? I usually remember it this way. How does this help us? Suppose we have a load connected, right? If it's like this, then we can write it out, right? The gain is equal to negative GM times the total resistance between the drain and AC ground, which is, this is the drain pin, right? AC ground is right here, isn't it? So there's only RD, making it negative GMRD. If there's an R load connected here to ground as well, then what would it be? There's RD connected to AC ground and RL connected to AC ground, so it would be RD in parallel with RL. I usually remember it this way. And what if it's connected to another amplifier stage? It's not difficult, right? If we connect another amplifier stage, what will we have? There's RD connected to AC ground, and then what else? There's the R input of another amplifier stage connected in parallel, right? Because it connects the drain to ground, and the other one connects to the R input, so this drain pin is connected to ground as well. Therefore, by following this approach, it will help us determine the gain much more easily. Hopefully, that makes sense, right? And for the overall gain, the signal source needs to enter directly into the input pin, which is this gate pin right here. It is a crucial step to ensure the signal path is correctly identified for our analysis. So we can write that from the definition, the overall gain equals Vout divided by V signal, right? Which we can write as being equal to Vi divided by V signal multiplied by Vout divided by Vi, right? We can see that it's a ratio, right? And what is Vout divided by Vi? It's the gain itself, right? So I can write it out as having Vi divided by V signal on one side as a single equation, which is R input. It's read as R input times R signal multiplied by the gain. R input depends on the topology, meaning how much R input that amplifier has, but the equation Vi divided by V signal will always be equal to this. This is the reason why we don't need to memorize what the equation for the overall gain is. Just remember that it equals this value. The R input for each topology changes, right? In this case, the R input is equal to infinity. Therefore, the overall gain is equal to the gain of the amplifier itself. I hope this doesn't confuse you. This is the common source configuration, and its direct counterpart would be the common emitter, right? Now, looking at this one for the common emitter, you will notice that the circuit appearance is actually quite similar. For this one, the supply is called VCC. Let's take a look at how we draw the topology supply. This connects to the drain pin, so we set the DC supply as two capital Ds, VDD. This is also a DC supply. This one is written as VCC, and there will be an RC connected to the NPN transistor. The emitter pin goes to ground, and the input goes into the base pin like this VIN. This specific point here is the Vout node. Now first, let's take a closer look at the R input. when we are looking directly into this pin, the R input equals, well, let's break it down. Since the emitter pin is connected directly to ground, when you are looking in, you only see the RPI resistance. So is the R input equal to 4? Let's verify that calculation together. Okay, so 4 is definitely the correct answer here. And if we look at the R output, tracing it back into this specific output pin, we can see that the value will be exactly equal to RC. It is a straightforward relationship, and here we have the collector resistor, RC. Now, what about the voltage gain? Well, the gain will be equal to minus GM multiplied by the parallel combination of these resistors. Let me just copy this part over here for clarity. As you can see, it is equal to the exact same expression we derived earlier. It really is quite straightforward once you break it down step by step. So this calculation will ultimately be equal to the total resistance of the circuit. To be more precise, this value will be equal to the total resistance measured specifically between the collector node and the AC ground reference point. It is important to remember that while we are focusing on the AC ground here, the AC ground and the DC ground are often treated as the same potential in many circuit diagrams, though they serve distinct purposes in our analysis of the signal path and the overall stability of the system. These are the same point, meaning they are both ground. So what does this mean? It means that for this one, we can find the gain, which is equal to negative GM times RC, right? If there is an RL, we can write it as negative GM times RC parallel RL, right? Is it easy? If you remember it this way, it's definitely much easier, right? And for the gain, I can write it out like this. It's equal to Rin divided by the sum of Rin plus R signal. And then all of that is multiplied by the gain. Does that make sense? It's a straightforward way to break down the equation. And then you can fill in the equation yourself. Our input is just RPI, that's all. It's not difficult. I hope it's not too hard for you all. Alright, moving on. Let's start by analyzing the BJT part first. We'll be looking at a common emitter configuration with an RE connected. Now let's see, if we connect an RE, the overall properties of the amplifier will generally improve, leading to better stability and performance. The part that really gets worse here is the gain, as is usually the case in these configurations. Let's look at the setup. We have VCC up here, right? We have the RC resistor connected here to the N channel, which is then connected to the NPN transistor, and of course there is an RE resistor located right here. The input signal is still exactly the same as before, entering at the base pin, and the output signal is also still the same, exiting at the collector pin. Now, having established that, what about the R input? What exactly will the value of R input be in this specific circuit arrangement? Let's take a moment to figure that out. Once you have a resistor connected to the emitter pin, it will always cause the input impedance of the BJT to increase, which is a fundamental characteristic of this specific circuit configuration. How much higher does it get? It's the total resistance on the emitter side multiplied by beta plus 1. I can write it down here. You'll need to memorize this. I don't know any other technique for it. Whenever there is an R on the emitter side, the input impedance will increase by a factor of beta plus 1. So it can be written as beta plus 1 multiplied by RE plus RE. And what about the R output? It will still have the same value as RC. Let's take a look. We have already derived the equation for how to find it. Moving right along, the next parameter we need to determine is the gain, right? So let's break that down. The gain is mathematically equal to negative alpha multiplied by the total resistance that exists between the collector node and the ground. And honestly, I'm just a bit too lazy to write out the full EDC ground notation right now, so bear with me. Now, all of that is divided by, let me be precise here, is divided by the value of RE plus the total resistance that we find between the source. Wait, no, scratch that, that's not the source. Let me reevaluate the circuit diagram here to ensure we are looking at the correct resistance path. So looking at this circuit, this is a BJT, right? We have the emitter connected directly to the ground. Now, when I'm trying to recall the bias voltage for this setup, I usually tend to remember it as the resistance at the top divided by the resistance at the bottom. It's a simple way to keep the voltage divider rule straight. If the resistance R here is significantly greater than the emitter resistance Re, then we can simplify the calculation and approximate it as RC divided by the Re located directly below the emitter, right? But of course, that is just a rough approximation. During our university studies, it is really important that we try to focus on remembering the correct, precise equations first before relying on these shortcuts. Okay, so we have covered 2 or 3 of these configurations now. Next, let's take a closer look at the MOSFET ones. For the MOSFET, right, it is essentially like having a left arm and a right arm working together. Specifically for the MOSFET, there will be a common source terminal connected to the source resistor, RAS. Because of this specific arrangement, the resulting circuit diagram will look something like this. In this circuit configuration, we have the VDD supply voltage connected directly to the resistor RD, which then feeds into the drain pin of the transistor. Moving on to the source pin, we can see it is connected to a resistor specifically labeled as R source, which provides a path to ground. Regarding the control signals, the input signal is applied directly into the gate pin, while the final output signal is conveniently pulled from the drain pin. This is the same as before, we've already analyzed it, the R input. This is still equal to infinity, just like before, right? The R output. This value is exactly equal to the resistance RD. Now let us consider the gain of the circuit. What about the gain? Well, the gain of this amplifier will be equal to, let me think, it is actually the same as what we calculated before. So there is no change in the overall amplification factor. It will be the ratio of R. To determine the overall gain, we first need to look at the total resistance present between the drain terminal and the ground. This value serves as our numerator. Then we divide that entire figure by the sum of 1 over the transconductance, or 1 over Gm, plus the total resistance that exists between the source terminal and the ground. When you look at this specific configuration, you can clearly see that the resulting gain, especially when we consider the placement of the resistor R, is actually quite similar to the gain characteristics you would typically observe in a standard BJT circuit configuration. It is a very useful parallel to keep in mind when analyzing these types of amplifier stages. The drain can be compared to the collector pin and the source can be compared to the emitter pin, right? And 1 over Gm is also close in value to Re. Do you see the similarities now? I hope this helps you remember it better. The gain is equal to I input divided by I input plus R signal multiplied by the gain, which is equal to the actual gain. Because I input is equal to infinity, infinity divided by infinity equals 1. This is still the first topology, it's all common source. That is, from this common source, we connect RS. Now we can see that the I input, as you can see, has increased in value. Because this I input is just Rn. Now there's beta plus 1 times Re, which is Rn, right? This term is Rn. And then we have this specific term, which also increases in value as we proceed. And that is actually a very positive development for our calculations. Now, moving on, this represents the second topology that we have studied in this course, which is known as the common gate configuration for MOSFETs. It is important to note that in the diagrams we have seen so far, they did not draw out the full, complete circuit, which is something we should keep in mind as we analyze these systems further. It's not exactly that they didn't draw the full circuit, they left out 1 R. So in this case, I will draw it completely because before we look at the small signal, we need the MOSFET to be in the saturation region, right? So the circuit will look like this, VDD. Now, let's begin by identifying the components. This resistor here will be RD, and then, in addition to that, there will also be an R source resistor connected directly to ground. Now, moving our attention to this gate pin, you'll notice that it is connected to ground, right? And the signal input will be applied around here, while the corresponding output signal will be taken from the drain pin. So this point here will be our V input, and this point over here will be our V output. Normally, if we were to draw out the entire DC bias circuit for this configuration, we would usually bias it in this specific way, and then connect an R2 resistor right here. You might be wondering, how exactly is the gate pin made to go to ground in this setup? Well, it is accomplished by using another capacitor which is connected to ground in this manner, effectively providing a path for the signal while maintaining the DC bias conditions. This is what the actual circuit looks like, right? Most of the time, it's biased like this. I'll erase this red part, okay? I'll erase it because it might get in the way later. Well, not exactly get in the way. But once we study biasing, you'll see for yourself that the bias circuit looks like this. Now, let's take a moment to look at these same terms once again, shall we? First, let's focus on the R input. This term represents the input resistance. Now, the R input follows this relationship. For example, specifically, the R input is equal to 1 divided by GM. This is a key concept to keep in mind. Actually, if we connect it this way, what will the value be? For R input, we have the source side going to ground, right? And we also have this RS going to ground as well. This R is also in parallel with RS. So if we choose a large RS, right? R input will be approximately 1 over GM, that's it. Okay, I hope this doesn't cause any confusion. What about R output? The R output of the op-amp is just RE, that's all. I hope this is understood, right? If we choose, because in the DC bias circuit, right, we have to make sure the MOSFET is in the saturation region. It's necessary to have current flowing like this, so it has to go down here, right, to the ground. In that example, we didn't have this RS, the topology we were working with. We connected directly to the R signal here, but in reality, we have to make sure the MOSFET is in the saturation region first, right? So there must be a current path to the ground for it, which is through this RS component. I hope I haven't made things even more confusing for you. And when we choose the value for RS, we just make it greater than 1 over GM, maybe 10 times or 100 times, that's all. This can be approximated as having a value of 1 over GM, right? Because when resistors are connected in parallel, the total resistance will be close to the smallest resistance value, correct? So it's about that. And I truly hope that you all understand this concept clearly. Alright, let's continue our discussion. We have already successfully calculated the gain, which is equal to GM multiplied by the total resistance between, well, what is it exactly? It is the drain and the AC ground. If a load is connected to the circuit, then it is RD in parallel with RL, right? Now, what about the overall gain of the system? As you can clearly see, the gain of this specific amplifier is essentially the same as the common source configuration we discussed earlier. It is important to keep these relationships in mind as we move forward with our analysis of these amplifier circuits. However, there is no negative sign, which means this configuration has a high gain, but the overall gain is low. Why? Because of the low input resistance. So we can write this as RIN divided by RIN plus R signal multiplied by the gain. You can go ahead and derive the equation for this yourselves. Next, let's look at the BJT version. This one has a common gate, and the BJT version is not to be outdone. Next, let's take a look at the common base amplifier configuration, which is actually quite similar in its fundamental nature to the previous setup. In this specific circuit arrangement, the supply voltage VCC is directly connected to the collector resistor RC. This resistor then serves as the critical link that connects to the collector terminal of the NPN transistor, which you can clearly see positioned right here in the middle of the schematic diagram. And this part here is what we call RE. This is the output. We start with the input signal, which we label as Vin. The very first step in our analysis is to determine the input resistance, known as R input, and we do this by carefully looking directly into this specific port. When we analyze this specific circuit configuration, we can clearly observe that the small signal resistance Re is effectively placed in parallel with the external emitter resistor Re. Moving forward to examine the output side of the circuit, if we look directly into the output terminals, we can determine that the total output resistance is simply equal to the collector resistor Rc. If we are looking at this specific bias circuit, you will find that it behaves in a way that is quite similar to the common gate configuration we discussed earlier. Now, moving right along to the next step, let us take a moment to carefully write out the full mathematical equation for the gain of this circuit. It is essentially equal to the transconductance, or GM, multiplied by the total effective resistance found between the collector pin and the AC ground reference point. Interestingly, if you look closely at the underlying math, you will find that this is exactly the same equation we use to describe the gain in a standard common source amplifier configuration. But its overall gain will be low, right? Because the R input is low, that's why We can write the equation like this. R input can be written similarly to the MOS one. If we choose a sufficiently large RE value, the R input will mostly be close to just RE, which simplifies our analysis significantly. Okay, so we're almost at the end of this derivation. The final configuration we need to discuss is known as the common collector, although you will find it is far more frequently referred to in engineering circles as an emitter follower. Now, you might be wondering, what exactly does this specific circuit topology look like when we lay it out? To visualize it, imagine we have our standard voltage supply connected to the system. In this particular setup, you will notice there is typically no resistor placed directly at the collector pin itself. Instead, the defining feature is that we have an emitter resistor, or RE, positioned right here in the path. Finally, when we look at how the signal is processed, for this specific configuration, the input signal enters the circuit directly at the base pin, which is a key characteristic of how this amplifier operates. So this right here will be the V input, and this will be the V output at the emitter pin. And finally, we have the R, or the resistor, that we have been working with throughout this entire process. This one is given as R, right? So if the bias circuit is like this, the R load will be connected in parallel with the RE. Alright, let's take a look at this further. At that time, when we were conducting our initial analysis, we made sure to include it in our scope. You can see there is a distinct R signal located in this specific area, and alongside it there is also a V signal, right? Those are the two components that we really want to amplify, and they are connected together just like this. And how exactly do we go about doing that? Let's look at the R input looking into this amplifier. Remember, I said earlier, if there's an R here, what does that actually mean for our circuit? It means the emitter on the side of the R. Specifically, the resistance on the emitter side will be multiplied by beta plus 1. So mathematically, it equals beta plus 1 multiplied by the quantity of Re plus R small a plus Re. This is a crucial step in understanding the impedance transformation happening within the amplifier stage. And if we look back into the R output of the amplifier, it will be equal to 1 over the transconductance, which is essentially the reciprocal value we are looking for here. No, that is not quite right. Actually, it is just equal to Re, nothing more. And if we take a moment to remember and we look back into it, right, there is actually another R output that we need to consider, right? So looking back into the R output and then carefully looking through the load and finally looking back to the V signal, we can derive that it is equal to the Re plus the R signal, all of which is then divided by the quantity of beta plus 1. We just did this, right? We can see that this is a voltage buffer, right? Looking from the load back to the R signal side, it causes the R connected to the base pin, which is on the input voltage source side, to be reduced by a factor of beta plus 1. But if you look from this side, you will see that all the R values will be increased in size, which means they are multiplied by beta plus 1. You need to remember this point. Looking from the input side, don't forget this is an emitter follower. Looking from the input side, the load resistance is increased in magnitude by being multiplied by beta plus 1. If you look from the output side towards the input side, the input resistance connected to the base pin, this will be reduced by a ratio divided by beta plus 1. I'm not sure what technique I can offer to help you remember this, but just know that for voltage buffers, when looking from the input towards the load side, the value increases by a factor of beta plus 1. Conversely, when looking back from the load side towards the input side, the resistance connected to the base pin is divided by beta plus 1. So you can look at it from two directions. So what do we do next? I'll try to write it out as an equation to indicate the positions, okay? So this calculation ultimately leads us to a very specific conclusion regarding the gain of the circuit. Now, how should I best express this mathematically? Well, the gain is essentially equal to the total resistance that exists between the emitter terminal and the AC ground, and we need to take that value and divide it by the emitter resistance, which we call Re, plus all of the other impedance factors that are sitting on top of that in the circuit configuration. Let me rephrase that for you to make it clearer. So essentially, what we are looking at here is that the total value is calculated by taking the base resistance and adding the total resistance that exists specifically between the emitter terminal and the AC ground point. This is a really important step because that specific resistance path plays a major role in determining the overall gain and stability of the amplifier configuration we are analyzing. So, looking at this equation, how can we write it out? It would be Re, right, divided by the sum of Re plus Re. Now, what if we connect a load? Let me go ahead and add a load in there. This one, right? We can just go ahead and write it out directly, if that works for you. I'll just go ahead and write it right here, using the exact same color pen for consistency. So if we use the simple principle of remembering the positions, right, that this is the total resistance between the emitter and the ground. Now, what's actually there? We have the emitter, the ground, and the ground. So we get it looking something like this, right? We have Re, then in parallel with Re, and all of that is divided by Re plus the one that I'm holding in my hand right now. It's a straightforward calculation once you visualize the path. Is it easy? So it'll be something like this, right? If you apply the principles of the various circuit positions I mentioned earlier, you might be wondering, what about the actual gain, specifically the overall gain, right? As I have said before, I usually remember the formula like this. It is the R input divided by the sum of R input plus R signal, and then all of that is multiplied by the intrinsic gain. And for this specific calculation, assuming there is no load resistance, or RL, connected to the circuit just yet, we can write it out in full detail as the final value is calculated as beta plus 1, all multiplied by Re, and then this entire product is divided by the sum of beta plus 1 multiplied by Re, plus another beta plus 1 Re term, and finally we add the R signal to that denominator. It is a bit of a complex expression to break down, but that covers the first part of our derivation, so that is one down. But like usually, which is equal to, it can be written in another equation form as well. It is equal to Re divided by Re plus R signal divided by beta plus 1. So from these two equations, we can see that this is V output divided by V signal, right? You can see that this is similar to the voltage divider circuit equation. It has three resistors connected together, right? Beta plus 1 Re, beta plus 1 Re, and R signal, right? If we think about it this way, if we think from the load side, right? This is the same, there are 2 or 3 resistors as well. Re, R signal divided by beta plus 1. This type of circuit is so. If we look closely, this equation is actually quite similar to the principles behind a standard voltage divider circuit. This is useful because it allows us to systematically draw the corresponding Thevenin resistance circuit. Once we have that structure, we can see it effectively has a value equal to our R signal, and it also incorporates the R component, just like we have illustrated here, right? This is the Re, and here we have the Re. Furthermore, there is an R signal that is being divided by beta plus 1, or you can write it this way too, no problem at all. Okay, right? This, I honestly don't know if it makes it more confusing or not for you. I think that's pretty much it. Oh wait, there is actually one more for MOSFET, right? MOSFET, right? I just want to make sure we cover everything clearly before we move on to the next part. Yes, for MOSFET, this has emitter follower. For MOSFET, it would be common drain, or what we call source follower, right? Why they call it this? It should have all been covered in the slides already, right? The circuit diagram will look similar to each other. This would be RD, which is VDD connected to. Oh, I am sorry, let me clarify that. Usually in this specific configuration, the term drain does not actually have an RD resistor associated with it. Instead, there is an R here, which is an R source connected directly at the ground. We have an input signal coming in, and the output is taken directly from the source pin. So looking at the S, or the source terminal, that is where the signal path is actually being directed. Signal voltage, we use pink, right? It will be at. So let's take a closer look at this specific circuit configuration. First, consider the R input. It is effectively infinity, right? To be more precise, the R input at the gate pin is considered to be infinite, because in this ideal scenario, there is absolutely no current flowing into that terminal. Now moving on to the R output, we need to determine the R output of the amplifier itself, which in this particular setup will be equal to the resistance we see looking back into the drain terminal, 1 over GM, and in reality it also has to be in parallel with R as well. Right here, how exactly should we look at this situation? If we really want to take a step back and look at it in the broader context of everything that has been happening, we need to consider the implications of these specific factors as well. This course, right? This part belongs to the amplifier. So we look back up at the A amplifier alone. This is like being a load, right? So the R output is equal to, so we start with the term 1 over GM. And then what's next? We need to write out the expression for the gain. The gain is defined as the total resistance between the source and ground divided by the sum of 1 over GM plus that same total resistance between the source and ground. Now, if you look closely at this formula, you can see that it can be directly compared, right? It's very similar to what we see when we look at the relationship between the MOSFET gate and the BJT. Just now, I was trying to break this down for you because understanding this ratio is crucial for analyzing the circuit's behavior. Essentially, the gain is determined by this voltage divider-like structure where the source resistance plays a dominant role. By comparing these two, we can better grasp how the MOSFET operates in this specific configuration, which is a fundamental step in our analysis. It really highlights the underlying principles of how these components interact within the circuit, and once you see the parallel, it becomes much clearer why we structure the gain equation this way to connect the load, right? So this one, let's try using the formula to solve this. I think there is a load here, Re, so we can write that out clearly. I will use the color first, using different colors. Sorry about that. So I can write that the gain is equal to what? It is R's in parallel with rim divided by 1 over GM plus R's in parallel with rim, right? And this is almost finished, right? There is only one step left to complete. The overall voltage gain is equal to rim divided by rim plus R signal multiplied by the gain. And I apologize, I forgot to write it out, but it equals the gain. Let me just take a moment to write that down properly so we can see the full expression of the amplifier. This is a summary of everything we have learned so far. It is essentially all about one particular parameter that defines the overall performance. We have carefully examined how this specific component influences the final output quality. Here of notes, I hope it helps. As I said, it is important and what I am trying to write down. Try to take a good look at it. Actually, it's not that hard to memorize. If you know the positions and everything, I hope that everything I've been trying to tell you will help you have a technique for memorizing in a certain way.